Hello everyone. In this video of vibrations, we are going to talk about dynamic vibration absorbers and tuned mass dampers. Both of them are methods for reducing or eliminating vibrations in a system that is very sensitive to vibrations, and also the frequency of excitation might be close to the natural frequency of the system, so the system is going to show a resonance, which could be very dangerous. You all probably have seen the video of Tacoma's Narrows Bridge, right? Where a basically not super strong wind could excite the torsional vibration of the bridge and made it collapse, right? So there are lots of applications where you cannot afford to have large oscillations of the system. For instance, you might see in chips, right, in circuit boards and so on, you might see something like this, what we call an inertial ring, and you might say, what is this? What did they add this kind of ring on the top of all of these circuit boards, right? Well, that acts as a vibration absorber. Or if you, for instance, look at the Type A 101 scraper, right? You see that at like the 90 or 91st floor at the very top of the tower, they have this huge mass, right? Which is basically about 660 tons mass damper. Why do they do that? They want to absorb the oscillations of the building against wind and earthquake. Okay, so I want you to know a little bit behind the scene. What is the theory of this, and how is it that these systems are working? Okay, so I explained them. I explained the difference between them a little bit, and hopefully with some MATLAB demos that I'm going to show you, you can have a better understanding of this topic. So first, the dynamic vibration absorbers, or DVAs, and the tuned mass dampers, or TMDs, are closely related topics, okay, or techniques for eliminating or minimizing vibrations, but they are not exactly the same. The core principle for both of them is the same thing. First of all, they are passive methods. So you add what we call a mass spring damper or mass spring system to the original one, and that is a passive system, so you don't change any of their properties. And by adding this extra mass spring or mass spring damper system, your goal is to use counter forces of this new system, okay, to cancel the force of the original system, or in other words, we call it destructive interference, to reduce or eliminate vibrations. If you want to look at it in simple explanation, the dynamic vibration absorbers are like a counterpunch, right? So you hit an object on one side with a punch, on the other side you hit it with a counterpunch, and hopefully if your counterpunch is strong enough to cancel the original punch, then that object is not going to move. The important thing about it, it works for a specific frequency. So when you design that system, when you decide the mass and spring for that system, you choose mass and spring, as we'll see in a second, to basically exactly work against a specific excitation frequency. So if that frequency changes, your system is not going to work as effectively, or might not work at all. I mean, to a good extent. But the tuned mass dampers, not only you have a mass and spring, you also add a damper. So the only difference is you will also add a damper, and the goal is it can minimize, it cannot completely eliminate, but it can minimize the vibrations for a bigger range of frequencies. So if the excitation frequency changes, the system can still work. The goal is not to completely get rid of vibrations, but to minimize it. So here I provided a table summarizing the difference between these two. So in DVA, I can say that the system is typically undamped mass spring, while in TMD, there is mass spring damper. The DVAs, as I said, is typically effective at one narrow range frequency or very small change in it, but TMDs can work over a bigger range of frequency because they have damper. The goal of DVA is to eliminate the vibration at that frequency. The goal of TMD is to reduce vibrations from a range of frequencies. The applications of DVAs, you can see them in precision tools, in rotating equipment, and in machinery. TMDs are used more inclusively, like in buildings, as I said, under bridges, like in Millennium London Bridge. You have this guy as well. In cars, in engine mounts, you can see that in ships and so on, right? And the technique for energy dissipation here is basically there is no dissipation in DVA, it's just redistribute the energy, the counterpunch. But here you will dissipate the energy through the damper. So the control philosophy of DVA is, as I said, the counterforce based on resonance, while here is a damp resonance for stability over a wider condition. Okay, so although they look very similar in nature, and the goal is reduce or minimize vibration, but their mechanism is a little bit different. So now let's look at DVA and look at a simple system with theory. So here is mass M1 attached to spring K1, and it is oscillating, and the excitation force is F naught sine omega t. Now you know that if that excitation frequency omega is equal to omega n for this system, which is a square root of K1 over M1, then you're going to get infinite response, right? You're going to get extremely large response. Even if there is a small damping in the system that I have not modeled, still you're going to get some big resonance. You're going to get some big vibrations, and that is what you want to eliminate. So what would you do? You add a secondary mass, which is your absorbing mass, and with the spring you connect it to the target mass that you want to minimize or eliminate its vibrations. Okay, so you add M2 and K2. The question is, how much would you pick for M2? How much would you pick for K2? So, first of all, before we answer that question, let's look at the equations of motion for the second DOF system. Because for the first DOF, it's very easy. Mx double dot equals F naught sine omega t, and then minus K1 times X, or X1. But now that you have X1 and X2 for object with mass M1, you have M1 times X1 double dot equals F of t, which you have, and then you have the spring forces, right? And these are the spring forces. Negative K1 X1, which is on the right side, you can bring it to the left, and then negative K2 X1 minus X2 on the left, which you can bring it to the right, from the right side, you can bring it to the left and make it positive. Okay, so if you have these two forces on the right side, they are negative, you bring them to the left side, they become positive. And then for object M2 is just the spring force on the other side, and that's equal to its acceleration. Okay, so these are the equations of motion for these two objects. Good. Now, I claim that if you pick K2 and M2 such that the square root of K2 over M2, which is the natural frequency of the M2K2 system alone, if you pick that such that that is equal to your excitation frequency omega, then guess what? If you excite this system with this force F naught sine omega t, guess what's going to happen? This mass M1 is not going to move at all. It's just going to go stationary. As opposed to having a big resonance, it's not even going to move. And mass 2 instead is going to go up and down. Now, is mass 2 going to go up and down with super large displacement? Not as big as M1, but clearly it is going to eliminate the motion of M1. So first of all, it makes M1 stationary. 2, M2 will go up and down, of course, not with as big as response as M1, but typically this M2 is the one that is not affecting the rest of the system, right? So here, if this guy moves a little bit inside this empty chamber, it's not going to affect so much, but the important thing is the building where the people are living, okay? So now, where does this claim come from? Let's see if this claim is true, because I just said, yeah, you pick K2 and M2 such that this equality holds and everything is going to be good. Well, let's find out. So in this system, the steady state sinusoidal solution, because your external force is sine omega t, so the solutions are also going to be something times sine omega t. And because there is no damping, that phi that we had in our solutions in the previous lectures when I talked about vibrations of 2DOF systems, that phi is not going to be there, right? That phi is not going to be there because, or phi 1 and phi 2, because there is no damping. So the only difference between x1 and x2 solution are their magnitudes, cap x1 and cap x2, okay? Yes? So if we consider these solutions and take two time derivatives from them, this is going to be x1 double dot, this is going to be x2 double dot. And now we can plug them right here and here, and the x1 and x2, I can plug them anywhere in these equations. And especially in the top one, if I plug in, right, and set the sine omega t equation coefficients equal, I get this equation. And if I plug it in the bottom one and set it to the, again, set the sine coefficients of sine omega t on the both sides equal, on the left side you have some coefficients, on the right side you have zero coefficients, so you get the second equation. There we go. So now you have two equations and two unknowns, and the unknowns are x1 and x2, and the known is of course f naught and the m's and k's and omega. So here you can solve the second equation for x2 in terms of x1, plug it in the first equation, and if you solve, you can get the solution for x1 and x2. Now remember, the goal was to reduce, or in this case, eliminate motion of x1. So what we want to focus on is x1. How much is x1? The amplitude of oscillation for x1. So x1 is obtained from this equation. You can get it from this equation, okay? Where you just divide f naught by this coefficient. Now, what happens to this coefficient when this condition that we wanted is satisfied? So now let's go in that equation, and wherever we have omega, we replace it with square root k2 over m2, okay? Or basically the square of it with k2 over m2. So I'm going to replace it with k2 over m2 here and here. And what happens? Well, if you look at this guy here in the brackets, or this inner term in the parentheses, you clearly can see that when omega 2 equals k2 over m2, this denominator becomes 0. And when this denominator becomes 0, that means this coefficient is literally going to infinity. It's going to be infinitely big. And when that is infinitely big, what does that mean for x1? x1 is going to be f over something infinitely big, so it's literally going to be 0. Do you see that? So if I pick my frequency like that, then the amplitude of oscillation for object xm1, which is called x1, that is going to be 0. Well, you might say, show me that with a simulation. There we go. So here is a system where m1 and k1 are these numbers, and omega is 7.05, which is exactly square root of 50. So if I apply a sine force with any magnitude and this frequency to only system m1 and k1, it is going to show infinitely big response. So now what do? I pick a smaller mass, like 0.1 of a kilogram, and then for K2, I solve for K2 from that equation that I have, right? Clearly from here, you can see that K2 equals M2 times omega squared. So I solve for I pick M2, solve for K2, and I get my K2, and then I'm going to apply a harmonic force with magnitude 1 with that frequency, and I'm gonna show you two separate animations. On the top one is basically the motion of mass m1, and on the bottom one is motion of m1 and m2 together. By the way, this frequency is not exactly equal to square root 50, right? So if you look at the square root 50, the number is 7.07. I picked it 705 because if it was 707, then I cannot show you the response of M1, K1 alone because that's going to be infinite. So I picked my frequency very, very close to natural frequency, so it shows a big, big response for the 1 DOF system, but now you can see that in the 2 DOF system, the effect is going to be different. So let's take a look. So here, the top one is motion of M1 alone. You can see that clearly it has very large amplitudes. Look how far it goes. It goes to like 3.3 or 3.4. It's huge, right? Of course, because your frequency is close to the resonance. And in the bottom one, look at the blue. Blue is still M1. It does not move at all. And the green one is M2, which it does move, but much less than this one that you can see here. Look, right? So I could go from that huge motion of M1 to no motion of M1 and a much, much smaller motion of M2. There we go. So you can easily see that how this system is working, right? Very easily the application of dynamic vibration absorber can be seen in this video, in this animation. And by the way, I'm going to share this with you so you can take a look at that as well. Now, what about the tuned mass damper, TMD? So this is very similar, except now you also add a damper to the system as well. And this can work for a range of frequency now. So this omega does not need to be a specific number. Even if that omega changes a little bit, because you added the damper, you can minimize, in this case, you can minimize motion of M1. You cannot eliminate it this time completely, but you can minimize it. And that's the goal. You don't want to completely take it away. You want to minimize it. In this building, when there is wind or earthquake, the building might move a little bit and it's fine, but you don't want it to move several meters or several feet to make the residents uncomfortable. So the way it is working, as I said, is it transfers the vibrational energy from the main structure to the secondary system, and the secondary system has a damper, so it dissipates the energy. Okay? Now here, the question is, if this excitation frequency is omega, or in this case omega t, how would you pick the values in the secondary system? So this excitation frequency, let's call it omega t, just to make it different from last case. And this omega t does not need to be a single number. It can be a range, but here we just pick a single number, like the average of that range. How would you pick C2, M2, and K2 so that the system works? Well, the formulas that determine these numbers are called the Den-Hartog's formulas. What are these? It says, if natural frequency of the first system is square root of K1 over M1, call it omega n, and the ratio of the absorbing mass to the target mass is mu, then here you define a ratio called F optimal, which is the ratio of two frequencies. And this frequency, this ratio, in the numerator of it, you have the omega of the basically TMD system over the original omega. And this ratio should be equal to 1 over 1 plus mu. Okay? So what does that tell us? So here we're going to pick some M2, like last time. We just pick some M2, typically much smaller than M1. Now, how much smaller? I'll tell you. The TMD system works best when the mass ratio is a little bit bigger than 0.01. So if you want to pick a mass M2, make sure it is about 100 of M1 or a little bit bigger. Okay? Yes? So make sure that, so this one can give you a hint of how much you pick for M2. Then what? Then once you have M1 and M2, M1 is already given, M2 you picked, you can determine mu. From mu, you can determine this ratio. And omega n is already known because your original system is known. That will give you omega of the tuned mass damper system. Now, omega of tuned mass damper system is equal to this omega of TMD, like previous case, that's equal to square root of K2 over M2. So once you have M2, and from this formula, because you have this side and you have this one, you can determine omega MTD, you can determine this. By squaring both sides and multiplying, you can get K2 now. There we go. So now K2 is determined. And finally, the optimal damping ratio for the system, which is C2 divided by 2 square root K2 M2, can come from this formula, square root of 3 mu over 8 times 1 plus mu cubed. And again, mu is known, K2 and M2 already determined. So from here, you can decide for C2. There we go, done. So once you pick your M2, C2, and K2, now your system is designed and you can use it, okay? So if I give you M1 and K1, you can, by picking a ratio for mu, you can determine all the 3 parameters and you can get it to work, okay? Now, it works best when the structure has a narrowband resonance, okay? So the resonance is only in a specific region and it's narrow, like a skyscraper or bridge. If the system has a broad range for big responses, then it's not as effective, and it works well when this mu is a little bit bigger than 0.01, okay? The good thing about the damping is damping broadens the range of the frequency. So if you see here, if you look at this, here everything is based on your omega t here, right? This omega t should be somewhere close to this omega n, correct? So it excites it big time. But even if it's not exactly there and a little bit around it, still the system is going to work. And to show you the effectiveness of that, here I show you this second code that I wrote. And this is the TMD demo. So here we have the system and the parameters are determined from here. And then here I'm going to show you again the response of system 1, which is only M1 and K1. And then I'm going to show you the response of system 2, which M2, K2, and C2 are added. And this time we're going to show the plot of their magnitude. So this is system 1. You see big magnitudes. And this is system 2, where the red one is magnitude of M1 and the blue one is magnitude of M2 here. Okay, and if you look at the magnitude of M1, you see that this is like, if you look at this, like 0.04 or something, correct? Maximum of it, right? So if you find the maximum is like 0.04, 0.05, no more. But here, the maximum is about 0.25. Okay, so it's about 6 times bigger. So it reduced the oscillation of M1 by a factor of 6 almost. Of course, max M2 now showing big displacements. But remember, mass M2 is much smaller than mass M1. And if you give it enough space within M1 or near M1, it is fine if it oscillates bigger and it is not going to affect the rest of the system. So here the goal is to minimize the motion, not completely eliminate it. You see that the red still shows oscillations, no zero motion. But it is passed to the blue system and the blue curve, and because that one has damping over time, it is going to reduce that energy, at least to a minimal extent that is possible. So as long as there is a harmonic force, both of the masses will move, okay, because you're injecting energy all the time. But at least your main system, M1, is not going to oscillate big time. So this is a demo for TMD. That was the demo for DVA. And that was the theory behind these two techniques. So I hope you learned something about them and you enjoyed this video, and I'll see you in the next lecture. Thank you.